Okay, now it is recording. Okay, now we're recording. All right, here we go. So, um, first thing I would actually point out, we're going to talk about chemical shift. You kind of need to be looking at your chemical shift table. Once again, like IR, there is a number of chemical shift tables out there. I don't recommend a lot of them. And the other thing about this, I'm going to be really, really emphatic. Again, something the way it was taught at Denison University, and they would teach people that the chemical shift table by functional group. No. When you look at the chemical shift table I've given you, I have highlighted in red just hydrogens. We're looking at the chemical shift ppm for a hydrogen. What you observe in a proton NMR are hydrogens, not carbons. If I wanted a chemical shift for carbon, those go in the realm of 0 to 200 ppm. You can begin to see how they are at different actual frequency. Okay? So we're always looking at a hydrogen relative to something. Okay? What is it? What's around it? So we can begin to imagine a chemical shift is determined by electrons. Electrons around this hydrogen that I'm trying to observe, and those electrons are essentially absorbing my magnetic field. The more electrons that are around something, the more the magnetic field is absorbed, and the weaker magnetic field that nuclei feels. Okay? So the nuclei feel a weaker magnetic field, meaning the difference between excited and ground is going to be smaller, lower energy, lower frequency. High frequency, high energy, low frequency, low energy. So the more electrons around that hydrogen, the lower the energy, the lower the ppm. Remember, because ppm is that magnetic, your signal frequency divided by the total magnetic field. So the smaller my hertz, lower energy, the lower my ppm. So when you look at an NMR spectra, or a chemical shift table for that matter, things that have more hydrogens around, I need to stop there. Things that have more hydrogens around them are going to have lower energy frequencies, lower ppm. Things that have fewer electrons around them and feeling more of that magnetic field, having a bigger difference between those two, a higher hertz, higher energy difference. Therefore, we're going to get signals that are much higher ppm. General term, when you see things at low ppm, we call that downfield, and it kind of seems backwards. And when you see things that are at higher ppm, you're going upfield. And so I don't even almost think about it that way. I look at my spectra, and I know the things that have the most electrons around them are to the right. The things with the fewest electrons around them are to the left. And I don't know that you can look at a molecule right now, an organic molecule right now, look at a hydrogen at the side. Yeah, that's going to go there. Okay? That's just not going to how it's probably going to work for you. So we need to go through examples, and we have a chemical shift table to help us with these kinds of examples. Let's take the simplest example first by looking at the very first NMR that you have on your packet of just NMRs, and the molecular formula for this molecule is written there, which is what C2H5Br, right? C2H5Br. So you already know just how many hydrogens exist in this molecule already, right? And you already know there's a bromine there. But the question is, how is that bromine affecting chemical shift? And why? Right? So on that spectrum, you're seeing two different peaks in two different regions. Now, don't get confused about the splitting that's happening there. You basically have two sets of peaks on that spectrum. Everybody see that? One that's at a ppm of around 1, and one that's at a ppm of around 2 or 3. I forget now. Yeah, 3.5. That's a lot further than I would have expected. But anyways, so which hydrogens do you think are closer to the bromine? Which hydrogens do you think are further away from the bromine? The ones with the lower, or sorry, the ones with the higher ppm are going to be closest to the bromine, but why? So the electron withdrawing ability of bromine, the electronegativity, right? It's pulling electrons away. There's less electrons around those hydrogens because of polarity. And as I'm withdrawing electrons away from it, now those hydrogens are feeling a much higher magnetic field, stronger magnetic field, and it creates a bigger difference, and therefore a larger energy signal and a higher ppm. That makes sense? So I'd like to start there, using something you should be fairly familiar with at this point, that halogens are more electronegative and create polarity, and that polarity creates a difference in where we see it on our NMR. All right? I'm going to lose my voice here. All right. So you could go to your chemical shift table. You see those peaks that are at about 3.5, and go to your chemical shift table and just go through your ppm until you find something that lands around 3.5-ish. And you'll find probably more than one option. If all those options make sense. Not really, right? You can't tell me it's a hydrogen on a carbon next to an oxygen if you don't have oxygen like the formula. You can't tell me it's a hydrogen on a carbon next to an iodine if you don't have an iodine. And so on. That makes sense? So, does the peak at 3.5 match up with the chemical shift table for a hydrogen on a carbon next to a bromine? See? You see that being in the 2.6 to 4.2 range. Right. Wow, it depends on what else is around those hydrogens. So some of these chemical shift effects can be additive. What's not on this table is what would happen if I had a benzene ring next to those hydrogens and a bromine. Right? Now the chemical shift gets even further out of that range even. So just be careful with that part of it. This is really trying to show you the effect of one bromine, not two bromines. Not when the hydrogens are in between a bromine and an oxygen or something along those lines. Yeah. So certainly fits with hydrogen and bromine. So that signal is telling me that much. Now, if you look at that particular peak, the integration is given below in the spectrum. And what is that integration for that peak? 2. That tells me what? There's 2 hydrogens that are kind of on the same carbon, same distance from that bromine. Look, I'm already building a molecule, right? Now, I've got another peak that's not next to the bromine, right? Because of where it's at. So how do you think I'm going to draw that? I know my molecular formula is 2 carbons, 1 bromine, and 5 hydrogens. So, well, let's put another carbon out there, right? And now we can imagine what's it look like to have a hydrogen that's here relative to there. Further away, less electron withdrawing, There's going to be more electrons around this hydrogen, therefore further upfield, and fits going to be around 1. In fact, if you look at your chemical shift table, hydrogens attached to carbons that aren't really near anything else are going to be the first thing you see on that spectrum, around 1. It's almost always around 1. So the hydrogens that aren't next to, and that's again, here's language I understood, hydrogens that aren't next to the functional group will show up closer to 1. Very rarely do they get too close to 0. To get much closer to 0, that's usually hydrogens on a carbon that are next to a silicon. That's what we use as our reference peak in our spectra. We use what's called trimethylsilane. It's got 4 methyl groups attached to a silicon. And silicon, for whatever reason, it's got more electrons around, and therefore puts it closer up, more upfield, and lands right at 0. That's kind of our reference peak that everything referenced in that TMS. All right. Well, then you go to the integration. What's the integration for that peak? 3. And so, well, put 3 hydrogens, and we can kind of see how these 3 hydrogens are all the same distance from that bromine and experiencing the same basic chemical shift. So they land in the same peak. So you have 1 peak basically with 3 hydrogens, and 1 peak with basically 2 hydrogens, and they fit chemical shift-wise. So I could draw this molecule legitimately from just the molecular formula. The chemical shift and the integration suggests this. Yeah.
Could you, on the carbon that's attached to the hydrogen down underneath, it's like 1 hydrogen above and 1 below, or no?
But we're not necessarily drawing 3-dimensional structure. But if you move hydrogens around in this structure here, is it a fundamentally different molecule? Nope. So you can move your hydrogens all over the place based on what I was reading yesterday. Pretty well. I still have a few people that like to do this. So I just want to point this out. How do you know it's not that? What's that? That's the first thing I would say. Don't ever draw bromine with 2 bonds. Just don't do it. And it's tempting, just don't do it. When it comes to doing reactions, don't put 2 bonds on bromine ever. Because you know what I'm going to say. Just feedback on your exam or your problem set right away. 2 bonds on bromine. Anyone wants you to put 5 bonds on a carbon, right? Or they put, I think it was the same person, went as far as putting 3 bonds on an oxygen, maybe 4. I can't remember. But it's sort of, oh, no. Let's write it in. Okay, write it in. 4 bonds on a carbon, no more, no less. 4. 2 bonds on oxygen, no more, no less. 1 bond on halogen, no more, no less. So you still want to use the same valence here when you're drawing a structure for NMR. Don't drawing a structure. You're still going to be separate. Okay? Now, what else would be incorrect here? These hydrogens are technically the same distance from that bromine as these hydrogens. They can both be down in that 3.5 range. And the final thing here is you also have a carbon without text. Yeah. So you then say, oh, okay, now that's what so don't do that. Don't do that either, okay? So you can see how we arrive at the structure from that NMR spectrum. Does that make sense? All right. Oh, we can see splitting in the spectrum too. That's the part I skipped. The splitting is not overall changing my analysis of that spectrum. But notice the splitting. Here, I have a carbon, 2 hydrogens on it. The next carbon over has how many? 3. Splitting with this first order goes by an n plus 1 rule, where n is the number of nuclei on the neighboring uh, carbon. So you can see here, next carbon over 3 hydrogens, n is 3. That means these 2 hydrogens will be split into 3 plus 1, 4 peaks. We call that, we go with singlet for 1 peak, doublet for 2, triplet for 3, quadruplet for 4, quintuplet for 5, and so on. But I'm not going to really try to overwhelm you with all that kind of terminology. So they end up when we report them, we just use an abbreviation. S for singlet, D for doublet, T for triplet, Q for quartet. I don't know if I see anybody do quintet on that reporting. So we go just put M, multiply it. It was a lot of peaks. Yeah. All right. So you can see this peak here, peak is 4. So you can see that peak at 3.5 now appearing as 4. On the flip side of that, you see that these are coupling with that. You look at this peak at around 1, integrates to 3, but now it's next to how many? 2. It's now 2. These 3 hydrogens will be split into 2 plus 1, 3. You get a triplet. Everybody see how the peak at 1.5 is a triplet, a 3. So one of the things I try to establish is when we see this quadruplet, triplet pattern, okay, whenever you see that pattern of